Good afternoon, everybody. I'll move on a bit from the electricity side of the energy system optimization, and I'll talk about how we can develop time-resolved linear models in the context of CO2 capture in industrial facilities. So the assessment and the design of CCS technologies typically involves two steps. The first one is the process simulation, where you go into the details of the thermodynamics and the chemistry of the process. And the second one is the techno-economic framework, in which you take the KPIs, the parameters from the process simulation, and you try to assess the overall economic performance of the system. And these two steps are typically performed under the assumption that the operations and the outside economic framework are either static. So, for example, you have static flue gas flow rate or static CO2 concentration or static electricity prices, or are dynamic, but in this case, generally with a very short time horizon, something in the orders of seconds or maximum minutes. However, in reality, industrial plants operate under dynamic conditions over a longer period of time. So here you have a profile with the emission profile of a waste-to-energy facility over 1 year, so you can see the variability. You can also see here the CO2 concentration in the flue gases in a waste-to-energy plant, which also fluctuates quite a lot. This is an example of a cement plant. This is the emission profile, and you can see how it goes on and off multiple times throughout the year. And you have also high variability in the electricity prices in the market. So the traditional techno-economic assessment is missing the potential interplay that there is between three key elements, which are the real-world temporal dynamics with the relative off-design conditions, the design characteristics of the capture unit, and the overall economic performance of the system. And this leads to the research question of our work, which is, can we develop time-resolved models to support the assessment of CO2 capture technologies for industrial facilities? Here is a brief overview of the rest of my presentation. So I'll start from the modeling framework, moving then on to the capture technologies and the industries that we are looking at. I'll show then some application and some results, and I'll finally draw the conclusions. So modeling framework, let's start from the needs. We said we want to model the longer time dynamics of the CO2 capture in an industrial facility. So we need at least a model that is able to handle something like hundreds of thousands of variables just for the time resolution part. We also want a model that is able to keep some of the physical fidelity of the process that we're analyzing, and we also want a model that allows us to identify the optimal design and operation of the facility. So for this reason, we found MILP to be the solution that was most fitted for the case. And let's now look at the approach that we're having. So the idea is that we start from detailed process simulation. So we performed multiple simulation, rate-based simulation in Aspen. And these simulations are both on design and off design, so to account for some variability that is not considered in the initial design. Once we conducted this multiple simulation, we have a sort of performance space, a series of data. We can linearize this space through some linear regressions, and we obtain a piecewise linear model for the capture unit. Now, once we have the piecewise linear capture model, we can embed it into a bigger MLP framework, which has an yearly time horizon with hourly resolution. And in this framework, we can have things like the CO2 concentration profile over time, the real-world industrial production profiles, the electricity prices, district heating demand, and also importantly, the interaction with other technologies. So for example, if we have industrial boilers or heat pumps or anything else. Now, for the model of the CO2 capture unit, we have three main domains of variables. The first one is refers to the technology selection. So which capture technologies is best suited for the specific industrial process. The second one relates to the design. So what is the optimal size of the capture unit for the process that we are looking at? And the third one relates to the operation of our system, so hourly operation. And this is what is the portion of flue gases that is optimally to treat and to capture every hour. Then we have some parameters. We have the capex of the capture unit as a function of the size and as a function of the design CO2 concentration. We have the energy input to capture the CO2 as a function of course, how much CO2 we are processing, the design CO2 concentration, and also the hourly CO2 concentration to account for these off-design conditions. Now let's move on to the cases that we analyzed. So we analyzed two industries. So the first one is the waste-to-energy industry, or service providers, better. And the second one is the cement industry. For the waste-to-energy, we have two capture technologies. We have a post-combustion MEA, and we have also post-combustion calcium looping system. For the MEA, we didn't do the simulation ourselves, but we are using the work of a former PhD in Matteo's group, Luca. For the cement, we have, again, the same MEA as the waste-to-energy facility, and then we have a partial oxy-fuel, either partial oxy-fuel only or a partial oxy-fuel with a small post-combustion unit at the end of the process. Now let's look at the process simulations that we did for the waste-to-energy case. We said we didn't do the MEA simulations. We took the job of Luca. So let's focus on the calcium looping part. For the calcium looping on waste-to-energy, we modeled a traditional calcium looping process that uses calcium oxide to capture, as a sorbent to capture the CO2. Then this sorbent is regenerated in the calciner. This regeneration needs to happen at very high temperature, and therefore you have waste heat at a pretty high temperature. So what's typically done in calcium looping units is to add a small power production unit to make use of this high temperature heat and produce some extra revenues for the system. So we said we performed multiple Aspen simulations. We performed the simulations for 3 plant sizes, a small, a medium, and a big one, and 2 targets CO2 concentration. We have 8% and 10%. And for each of these simulations, we have some KPIs, CAPEX, OPEX, net electricity production, and fuel consumption. We also simulated the off-design conditions, so with a flow rate variation of plus minus 7% compared to the baseline, and a CO2 concentration variation of plus minus 1% compared to the baseline. Now moving on to the simulations for cement, let's focus on the partial oxy-fuel with the small post-combustion capture unit. So we are talking about oxy-fuel combustion in cement. So the oxy-fuel happens in the calciner part of the cement plant, which runs on oxy-fuel conditions. And this allows to capture 80% of the CO2 in the gas stream, in the flue gas stream. If you want to capture the rest, so the 20% remaining, you can have a small post-combustion capture unit. Again, we performed multiple Aspen simulations, 2 plant sizes of the cement, 1,800 and 1,300 ton per day of clinker, and with different configurations, so with the partial oxy-fuel only and oxy-fuel with a small post-combustion capture unit. And again, we have some KPIs. We have CAPEX, OPEX, electricity consumption, and extra fuel consumption. Now let's look at some of the application of these models. Let's start from the waste to energy. So we will not look at the cement because it was too much stuff. So let's see the waste to energy and the MEA part. For this application, we are considering waste to energy CHP plant, so combined heat and power, which has as an input municipal solid waste, as an output heat and electricity. This heat and electricity can either be sold to the electricity grid, used to power the MEA capture unit, or used to supply the district heating demand. Then traditionally, a waste-to-energy facility has also an auxiliary boiler, which run on natural gas to supply extra heat in period of high demand. Now here you can see some of the results. So we run the optimization, and here you can see the optimal heat usage in the waste-to-energy facility throughout the year. You can see in different colors, different end use of the heat of the waste-to-energy plant. So you have in dark blue, you have the heat that goes to the district heating demand. In light blue, you have the heat that is used to produce electricity, which is then sold to the grid. In green, you have the heat that goes to the MEA, so the heat for the CCS. And then light green, you have the heat for electricity production for the CCS. And finally, you see a red line, which is the auxiliary boiler output. So when the boiler jumps in and produces some heat. And this is done for a certain district heating demand of 50% of the maximum output of the waste-to-energy. We can do this exercise for multiple district heating demand, from 0 to 100% of the maximum production. We will not go into the detail of these plots, but you can see that the optimal operation changes. And from this, you can also see what happens to the economics of the system and to the design of the system. Let's look what happens to the economics of the system, so the cost of capturing. Here you have the cost of capturing 1 unit of CO2 with the MEA, with the increasing district heating demand. You have in dark blue, it's the CapEx cost, light blue, the OpEx. In light green, there are the lost electricity revenues because you are supplying part of the heat to the MEA instead of using it to produce electricity and sell it. And in yellow, you have the extra cost of the boilers. And you can see that as the district heating demand increases, the cost for the boiler also increases quite significantly, and the electricity and the lost electricity revenues decrease. So the cost of capturing one unit of CO2 changes depending on the district heating demand. If we would do the same analysis with static models, we will not see any of these two behavior. We'll just see flat cost in any case. And the other thing that we noticed is that the optimal size of the capture unit is smaller when you have time-resolved models. So it's 88% when you include the real-time dynamics, and it's 100% if you would just do a static analysis. So it means that you are oversizing your capture unit if you don't take into account of the temporal dynamics. Now let's move on to the second application, to the second technology, which is the calcium looping unit. Again, on a waste-to-energy facility. So we have the same CHP waste-to-energy plant as before with the auxiliary boiler. Now this time, the calcium looping unit is a more independent unit because it needs its own fuel supply, which is this RDF fuel. It's a waste fuel that supplies the heat needed for the calcium looping unit. The calcium looping unit is also, we said, a small electricity producer, so it's also producing some electricity. And we have, again, the possibility of selling the electricity to the grid and meeting the district heating demand. Now, here we can see what is the optimal size of the calcium looping unit as a fraction of the maximum emissions for different electricity prices. So this is a sensitivity over the electricity price. And you can see that for low electricity price, the optimal size is very small. It's just 55% of the total emissions. The moment we increase the electricity prices, there is a sort of bump, and we go from an optimal size of 55% to 75%. And to understand why there is this bump, we need to look at what happens to the load factor, so how much you're using your calcium looping unit. And you can see that the moment you increase your size from 55 to 75%, what happens is that your load factor decreases significantly. So it goes from 98% to 93%. And this is because of the emission profile of the waste-to-energy plant. This means that if you want to capture more emissions, it's economically to do it only if you have higher electricity prices. Now, then we have also some implication on the cost of capture. We can see that the cost of capturing 1 unit of CO2 decreases with increasing electricity price. And we also see that this relationship is not fully linear, so we have some bumps here and there. So this was it for the application. So let's draw some of the conclusion. We saw that first of all, that the impact of a time-resolved model depends by industry and depends also by the specific characteristics of the plant. We also saw that time-resolved models, they support the assessment of capture technologies in both the technology selection, design, and operation. For the technology selection, I didn't show the results, but we did this extensively with the cement case. And overall, they help quantifying the trade-offs that we see and improving the overall economics of the system. Thank you for your attention. Do you have any questions?